So we're in section 12.4 now.
It's really awesome. Something about your body.
It's not funny.
So we're going to talk about tangent and normal vectors. So just to recap, what we saw in the last few sections when we were talking about differentiation of vector valued functions, integration of vector valued functions, and we applied that in the last section to the idea of acceleration and velocity. So if we have a curve, r of t, so we're going to say r of t is a vector valued function. We said that r prime of t is tangent to the curve. So it's tangent to r. And it's also going to point in the direction of increasing parameter. So our direction for r of t is in the direction of the increasing parameter. If we think of r of t as a position vector, that's what we did in 12.3. So if r of t represents a position, then we said that r prime is the velocity. So we could interpret the r prime as the velocity vector. Now this idea, this r prime is tangent to r and it points in the direction of the increasing parameter, that's true of any vector value function. We don't have to think of it as a position and velocity relationship. This relationship between r and r prime is going to be true for any vector value function. R prime is going to be tangent to the curve and it's going to point in the direction of increasing parameter. So what we want to do in this section is we want to talk about a unit tangent vector. So we're going to define these specific unit vectors that are going to be very useful when we're working with these curves. And the idea of a unit tangent vector, a unit normal vector, is going to be something that we use the rest of the semester really. So we're going to define our unit tangent vector. Since r prime is tangent to our curve, we're going to define t, our unit tangent vector, is going to be r prime over the magnitude of r prime. So that will give us a unit tangent vector at time t. And our only requirements here is that we're defining this on an open interval where r prime is not 0, and when we're saying r prime is not 0, that means that our curve is smooth. So we're defining this unit tangent vector in intervals where our curve is smooth. And the unit tangent vector, we've used, whether or not we realize it, we've kind of used the idea of a unit tangent vector in some of the problems that we've done. So let's talk about one example using the unit tangent vector, and then we're going to use the unit tangent vector to come up with our unit normal vector. So this one, we did a problem kind of like this yesterday. So let's say that we have at least one of the groups here, r of t, and this is given by e to the t, sorry, e to the minus t, 2 cosine t, and 2 sine t. So there's our vector. We want to find t, our unit tangent vector, and then we want to find a set of parametric equations for the tangent line at t0 equals 0. And we're going to use that to approximate r of 0.1. We're going to find our unit tangent vector first, and then we're going to find our set of parametric equations for our tangent line, and use that to approximate r of 0.1. We did. One of the groups did a problem like that. I think it was your group did a problem like that yesterday. But we didn't start out by finding t, but I want to make a kind of a connection to the problem we did yesterday. So to find our unit tangent vector, we need our, well, before we find our tangent vector, what kind of motion, what kind of, if we think of this as a position vector, what kind of motion is this describing? Not a cycloid.
Helix.
Okay, Ryan says it's a helix. In the YZ plane, if we project this onto the YZ plane, what does 2 cosine t, 2 sine t give us? Circle. So on the YZ plane, our projection is a circle. And then this e to the minus t, what is it telling us it's doing along the x-axis? So it's stretching, but we have an e to the minus t, so is it compressed away from the x, or away from the YZ plane, or compressed towards the YZ plane? So where are the circles going to be closer together? Further away from the YZ plane, or close to the YZ plane?
I have no closer.
Oh, sir, as t increases, is it going to be closer or further away? As t increases, how does x change? More and more, or less and less?
Less and less.
Less and less. So is it going to be compressed towards
Away.
or away?
Away.
As
I still away.
towards. So because closer to the YZ plane, what's happening to x? As t changes, is x changing a lot or very little? Very little, right? As we get further and further away, x changes more and more. Does that make sense? So we get this helix, and it's going to spiral. Around and around more as we get closer to the YZ plane. All right. So we're thinking about the geometry there. All right. So let's find our unit tangent vector. We need our derivative. We need our velocity vector. So r prime. What's r prime going to be here? We need to take some derivatives. Negative e to the minus t. What's going to be our y component? Minus 2 sine t, and the z component, 2 cosine t. And we need our magnitude of r prime. So the magnitude of r prime is going to be the square root of minus e to the minus t squared plus negative 2 sine t squared needs to go outside, sine t squared, plus 2 cosine t squared. And when I simplify this out, I get the square root of e to the minus 2t plus 4. So our unit tangent vector, t, is going to be 1 over e to the minus 2t plus 4 times r prime, e to the minus t minus 2 sine t two cosine. So there should be a square root here. Yes, thank you. So there's our unit tangent vector. And we want this, so this is going to be our unit tangent vector at any time on the curve. So it's going to point in the direction of motion. Our magnitude is going to be 1. Point in the direction of increasing parameter, or in the direction of motion, mean the same thing. Now we want parametric equations for the tangent line at t0 equals 0. So what are we going to do now? To get the equation of our tangent line. We need our direction vector, right? So what gives us our direction vector?
R.
What's pointing in the direction of the tangent line? R prime, or our unit tangent vector? Isn't that pointing in the direction of the tangent line at any point on the curve? So that's going to give us our direction numbers. So we're going to find t at 0. When I find t at 0, I get, this gives me 1 over the square root of 5 times negative 1, 0, 2. So this is going to give us our direction numbers. Do I need to worry for my direction numbers about this 1 over square root of 5 to get for my direction numbers for my parametric equations for my line? All I need is the vector pointing in the directional line. So I can use these for my direction numbers. So my direction numbers, a equals negative 1, b equals 0, and c equals 2. So my and for my tangent line, the equation of the tangent line, what else do we need for our equation of the tangent line? We need a direction vector and a point. So how are we going to find a point on this line at t equals 0? Plug in 0 into the original, into r. Our point is at t equals 0, so we find r of 0. R of 0, plug in 0 into my position function, and I get r of 0 equals 1, 2, 0. So here are my direction numbers for my equations for my tangent line. There's a point on the line, so the tangent line is x equals 1 minus t, y equals 2, and z equals 2t. This gives me, these numbers give me these things, and the direction numbers give me my coefficients on my t. And then if we wanted to approximate, use the tangent line to approximate r at t equals 0.1. Well, this is if we, at t equals 0, this gives us our point here at r0. So to approximate r at 0.1, so we're going to say r at 0.1 is approximately, I'm going to plug in 0.1 here, 0.9, 2, and 0.2. A little easier than calculating evaluating this position function at t equals 0.1. Now if we look back here, I just want to point this out. If we look back at our equation for our tangent line, our parametric equations for our tangent line, we could also write, and we talked briefly about the vector equation of our line, that our tangent line at t0, I'm going to write t, so t0 as a function of t, and let me not use t, let me use L, since my unit tangent vector is t. So our tangent line, our vector equation of our tangent line is r, our position at t0, that's what we did here, plus t times our unit tangent vector at t0. So I could have kept this 1 over square root of 5 in here. This gives me my direction numbers, and I multiply that by t. So I can use this as the equation of the tangent line at a particular point. R of t0 plus t times the unit tangent vector at t0. And that would give me parametric, that would give me a vector equation for my tangent line. So I just want to make a connection between what we've been doing with what we've done with lines before and this unit tangent vector. So questions on what we did there. So this isn't really anything that different than what we did in chapter 11 when we were talking about parametric equations of lines. We just start with a vector value function to give us something to generate our numbers for our tangent line equation. All right. So now we have a method for finding a unit tangent vector. Unit tangent vector is just our velocity vector divided by its magnitude. Points in the direction of motion, magnitude 1. What we want to do next is find a specific normal vector. In space, if we have some curve in space and we have a tangent vector, draw a little picture, and this is, we're thinking in 3 dimensions. If our unit tangent vector is here, we have an infinite number of normal vectors to that unit tangent vector. We just make it orthogonal. It could rotate around that unit tangent vector anywhere. So we could have a unit normal vector, an infinite number of unit normal vectors to this unit tangent vector. We're interested in one specific normal vector. So let's talk about this specific normal vector that we want. And our normal vector is going to be come in very useful when we start talking about more about the geometry of these curves. All right, so when we talked about the derivative, finding the derivatives of vector valued functions, we said that one of the properties of a vector valued function was that if r of t dot r of t equals 0, and I talked about this when we mentioned it, that this one was going to be important a little later, and I'm not going to say 0, I'm going to say c, a constant, where c is a scalar. So if our dot product is 0, then r of t, sorry, our dot product is a scalar, then r of t dot r prime of t equals 0. So that was one of the properties that we talked about when we talked about taking derivatives. And this is really easy to see. If we have, and I'm going to drop my t dependence, we know this depends on time, r dot r equals a constant. We're going to take the derivative. And if I take the derivative of a constant, I get 0, taking the derivative of both sides. And when I take the derivative of a dot product, what do I need to do? What do I use to take the derivative of a dot product? Product rule. So this is going to be r dot r prime plus r prime dot r equals 0. And we said that it doesn't matter which order we take the dot product in. So 2 r dot r prime equals 0. So r dot r prime equals 0. So what does this tell us about r and r prime if r dot r is a constant? R dot r prime is 0, so what does that tell us about the relationship between r and r prime? They're orthogonal. So if r dot r is a constant, then r dot r prime is orthogonal. So that means that r prime is normal to r. Makes a 90-degree angle. Well, we defined t prime, we defined t to be a unit vector. Our unit tangent vector t is a unit vector. So t dot t is going to be what? And what specific constant would this be? And the magnitude of t is 1. It's a unit vector. So t dot t equals 1. So by what we just talked about, t so t dot t prime is 0. So t prime is orthogonal to t. So we normalize t prime So we're going to normalize t prime to find what we call our principal unit normal vector. And I'm going to switch the page here. So because t is a unit vector, t dot t equals 1. So t dot t prime is 0. That tells us that t prime is normal to t. And we're going to normalize t prime and define that as our principal unit normal vector. And we call this capital N. N of t is t prime. And let me make the time dependence here explicit. T prime over the length of t prime. And we want t prime not equal to 0. And we want r because we defined t where r was smooth, so r represents a smooth curve. The principal unit normal vector points to the concave side of the curve. And we could also think of it as pointing in the direction that the curve is turning. So our principal unit normal vector comes from normalizing t prime, and it's going to point to the concave side of the curve or point in the direction that the curve is turning. Now, because of the way that we've defined this principal unit normal vector, where we take the derivative of t prime and we divide by the magnitude of t prime. Well, t prime, we had to normalize the velocity vector. So we have these, when we take these, the length of those, we end up with these radicals in the denominator. So you can imagine that finding n of t using this definition can get a little, the algebra can get kind of, can be a lot of work. So we want, sometimes it can be difficult to calculate this principal unit normal vector. We'll talk about some ways that maybe we can shortcut it in certain situations. But because of the way we defined it, it does get a little bit messy to find these things. So let's look at a quick example of finding a principal unit normal vector, and then we'll talk about a shortcut that we can use in certain situations. So questions about how we define this. So what we're going to do with the unit tangent vector and the unit normal vector is in the next section, the next thing we're going to talk about is thinking about the acceleration on our curve, and we're going to talk about a tangential component of acceleration and a normal component of acceleration. And we're going to use our unit tangent vector and our unit normal vector to help us with those concepts. The acceleration that goes in the direction of the curve, and this acceleration that goes normal to the curve, and that's going to lead us into the idea of the curvature, and we're going to be able to quantify curvature of a curve at any given point, which is kind of nice. All right, so let's look at an example of finding a unit normal vector. So we want to find n of t at t equals 2 for r of t equals ti plus 1/2 t squared j. So we just have a curve in the plane rather than in space. So we have to find in order to find our unit normal vector, we have to find our unit tangent vector first. So we're going to go through the process of finding our unit tangent vector. We need r prime. R prime of t is I plus tj. And then we need our magnitude to find our unit tangent vector. So the magnitude of r prime is going to be the square root of 1 plus t squared. So our unit tangent vector at any time is 1 over 1 plus t square root of 1 plus t squared, I almost forgot the square root again, times I plus tj. Now to find our unit normal vector, we have to find t prime and the magnitude of t prime. And this quantity represents t. So just right away you can see that this is going to involve a little bit of work. So let's find t prime. So t prime. I'm going to leave this 1 over square root of t squared out front of the vector. And I'm going to use the product rule to do my derivative. So t prime is going to be 1 over the square root of 1 plus t squared. I'm going to do the first times the derivative of the second. So this times the derivative of this vector. So I just get 1 over square root of 1 plus t squared times j hat. Plus, now I'm going to do I plus tj times the derivative of this thing. So using the product rule. So I get, I take the derivative of this, I'm going to write out all the pieces, minus 1/2, 1 plus t squared to minus 3/2 times 2t times I plus tj. What's that? Oh, it should be 2/3. 3, did I do it upside down? 3/2. Right, changed the wrong 3. So there's our product rule. If I simplify this, and distribute, I get this is minus t over 1 plus t squared to the 3/2 I plus minus t squared over 1 plus t squared to the 3/2 plus 1 over the square root of 1 plus t squared all times j. So there's t prime. And we haven't even found the magnitude of t prime yet. So what I did, I'm not going to go through all the steps. But what I'm going to do here is we find a common denominator so we can simplify this fraction. So we can add these two fractions. We can write this in a little simpler form. After I go through this algebra of adding these two fractions, I can finally rewrite this as minus t 1 plus t squared to the 3/2 plus 1 over 1 plus t squared 3/2 j. So that's my unit tangent vector. Now if I had to write, that's the derivative of the unit tangent vector. If I had to write n of t, if I had to find n of t for any particular time t, I would have to find the magnitude of this vector and divide t prime by the magnitude of itself. That is pretty messy. So we're gonna simplify that by because the problem only asks us to find n at t equals 2. I'm going to find t prime at 2 and then find the magnitude of that vector. So this is t prime of t. T prime of 2. We get, got to hurry up here, minus 2 over 5 to the 3/2 plus 1 over 5 to the 3/2. This is I and j. The magnitude of t prime at 2 turns out to be, if I find the magnitude of this vector, it turns out to be 1/5. So finally, n Our principal unit normal vector at time 2 is this vector divided by 1/5, and I get minus 2 over the square root of 5I plus 1 over the square root of 5J. So we see, even with a relatively simple curve in the plane, finding n can be very difficult. Not difficult, just a lot of algebra involved. So let me give you really quickly a shortcut in the plane. If we have a vector in the plane, can anybody think of a quick way to find a vector normal to that vector in the plane? So let me draw a quick picture. So let's say that our components of our vector are a and b. What is the slope of this vector? How can we, the slope? Think even simpler. What's the slope of this vector? That's a magnitude. The slope? What is it? B over a. What's the slope of a perpendicular line? Negative a over b. Flip the x and the y. We're taking the reciprocal and changing the sign. So if we have in the plane, if r of t equals x of ti plus y of tj, an orthogonal vector is r of t equals negative y of t I plus x of t j, or y of ti minus x of tj. So we switch the x's and y's and change the sign on 1. We pick the direction of to get the principal unit normal vector so it points to the inside, to the curve, the concave side of the curve. So in the plane, to find a normal vector, you switch the x's and the y's and change the sign on 1. We could have done that same thing on the last example, and we would get the same answer. All right. Unfortunately, this doesn't work in space. Homework. All right, there you go.
I left him at my house. Like I picked him out. No. I'm going to talk to the class about it.
You can also find the homework if you didn't get it. It's on the sideboard or it's posted on my website. Have a good weekend, everyone. Enjoy 3 days.